Welcome, Cosmic Explorer. Tonight, let us journey together through time and space to explore one of the most profound and fascinating stories of all, the story of how the universe began. The Big Bang Theory is far more than a scientific idea. It is a window into our deepest questions about existence, time, and the laws of nature. How did everything emerge from what seems like nothing? How could a single instant give rise to billions upon billions of galaxies, stars, planets, and life itself? Together, we will look back nearly 13.8 billion years to the moment when time and space themselves were born and follow the unfolding of the cosmos, step by step, as it evolved from a seething fireball of energy into the majestic universe we know today. Before the Big Bang, there was no universe as we understand it. No stars, no planets, no light, and not even darkness, because there was no space in which darkness could exist. There was no time, no measure of before or after. There was simply nothing, not even emptiness. This is one of the hardest ideas for the human mind to grasp, because we are so used to thinking of nothing as a kind of empty space, but even that is already something. True nothingness is beyond our imagination. Yet somehow, about 13.8 billion years ago, something happened. From a point smaller than an atom, a singularity of unimaginable density and heat, the universe began to expand. This was not an explosion in space, but rather the birth of space itself, a rapid stretching and unfolding of the very fabric of reality. In the very first fractions of a second, the universe was an inferno of energy. Temperatures reached beyond what our minds can comprehend, trillions upon trillions of degrees. All four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single superforce, acting in ways no human equations can fully describe. In this unimaginable chaos, the laws of physics themselves were not yet as we know them. Then, in an instant so brief that it defies belief, the universe underwent an extraordinary transformation known as cosmic inflation. In less than a trillionth of a second, the universe expanded exponentially, growing from far smaller than an atom to something the size of a grapefruit or even larger. This inflation smoothed out any wrinkles or irregularities, leaving behind a nearly uniform cosmos, but with tiny fluctuations in energy density. These tiny differences, created by quantum fluctuations, would become the seeds of all the structure we see today, from galaxies to clusters to vast filaments stretching across the cosmos. As inflation ended, the universe continued to expand, but at a slower rate. In those first microseconds, the energy of the early universe began to transform into particles, quarks, leptons, photons, gluons, and other fundamental entities that make up the building blocks of matter. The temperatures were still so high that these particles existed in a kind of superheated plasma, colliding, transforming, annihilating, and reappearing again in a wild dance of creation. Within about 1 microsecond, quarks began to combine into more stable structures, protons and neutrons. These particles are the cores of atoms, the essential ingredients of ordinary matter. But even these were still immersed in an ocean of radiation, unable to join with electrons to form whole atoms because the universe remained too hot. 1 second after the Big Bang, something remarkable happened. Neutrinos, those ghost-like particles that hardly interact with anything, decoupled from matter and began to travel freely through space. Today, these primordial neutrinos still drift through the universe, almost completely invisible, a silent relic of that first second. Meanwhile, a slight imbalance emerged in the amounts of matter and antimatter. For reasons not yet fully understood, matter gained a tiny advantage. If matter and antimatter had existed in perfect balance, they would have annihilated each other completely, leaving only pure energy. But thanks to this slight asymmetry, a tiny bit of matter was left behind enough to form everything that followed: stars, planets, and living beings. By about 3 minutes after the Big Bang, conditions had cooled enough for nuclear fusion to begin. Protons and neutrons collided and fused to form the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium and beryllium. This brief but crucial moment is known as primordial nucleosynthesis. It lasted only a few minutes, but it produced the raw material that would one day become stars. For the next 380 years, the universe was a dense, hot, opaque plasma of nuclei, electrons, and photons. Light could not travel freely because it constantly bounced off free electrons, scattering again and again. The universe was glowing, but nothing could see through the fog. As the expansion continued, the temperature dropped steadily until, at around 380 years, the universe reached about 30 Kelvin. At this point, the nuclei could finally capture free electrons to form neutral atoms, mostly hydrogen and helium. When that happened, the universe became transparent, and light could finally travel without constant scattering. That ancient light is still traveling today, stretched by the expansion of space into microwaves, and we observe it as the cosmic microwave background. This afterglow is a kind of baby picture of the universe, showing us what the cosmos looked like only 380 years after its birth. When scientists study it, they see tiny temperature variations, the same fluctuations seeded during inflation that eventually grew into galaxies and cosmic structures. Thanks to missions like COBE, WMAP, and Planck, we now have incredibly detailed maps of this cosmic background, allowing us to understand the universe's age, shape, and composition with great precision. After this release of light, the universe entered what is often called the cosmic dark ages. There were no stars yet, only vast clouds of neutral hydrogen and helium drifting through space. Gravity began to gather these atoms into denser clumps, forming the first structures. Over hundreds of millions of years, these clouds collapsed further under their own weight until, at last, nuclear fusion ignited and the first stars were born. These first stars, known as population 3 stars, were very different from our familiar Sun. They were huge, hundreds of times more massive, burning incredibly hot and bright, and living extremely short lives. In their cores, they forged heavier elements such as carbon, nitrogen, and oxygen, which the Big Bang itself could not make. When these stars exploded as supernovae, they scattered these new elements into space, enriching the cosmos and allowing later generations of stars and planets to form. Galaxies began to take shape, gathering billions of stars together in magnificent structures bound by gravity. Over billions of years, these galaxies merged, collided, and evolved into the vast galactic clusters and superclusters we see today. A web of filaments and voids emerged, forming a breathtaking cosmic architecture on scales almost impossible to grasp. Our own Milky Way is one spiral galaxy among perhaps 2 trillion galaxies in the observable universe. It formed over many billions of years, building up its stars through countless mergers and bursts of star formation. Roughly 4.6 billion years ago, in a quiet region of one of its spiral arms, our Sun was born, surrounded by a disk of leftover dust and gas. From that disk, 8 planets and countless smaller bodies coalesced, including Earth, the only place we know of so far that hosts life. All the elements in our bodies, the carbon in our cells, the calcium in our bones, the iron in our blood, were forged in ancient stars that lived and died before the Sun was even born. In a very real sense, we are made of stardust, the product of billions of years of cosmic recycling. When you look up at the night sky, you are seeing the descendants of the Big Bang shining back at you across unimaginable gulfs of time. As modern astronomy advances, we have developed tools to look deeper and deeper into this history. Powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, allow us to see galaxies forming only a few 100 million years after the Big Bang. We can watch the cosmic dawn unfold, witness the birth of the first black holes, and measure how galaxies grew and evolved. Each new observation helps refine our picture of the Big Bang and the laws of nature that govern our universe. The Big Bang theory is supported by an extraordinary array of evidence. We see the cosmic microwave background, the lightest elements in precisely the abundances predicted by primordial nucleosynthesis, and the large-scale structure of galaxies matching the patterns seeded by inflation. We see the universe expanding today, confirmed by the redshift of distant galaxies, a discovery first made by Edwin Hubble in the 1920s. Taken together, these observations form one of the most successful and far-reaching scientific models ever created. Yet mysteries remain. The Big Bang theory describes what happened after the expansion began, but not exactly what triggered it. Did the singularity truly exist? Or is that simply a sign that our current physics breaks down at those extreme conditions? Some scientists think quantum gravity might one day explain the very first instant, uniting general relativity with quantum mechanics. Until then, the precise cause of the Big Bang remains unknown. Other questions challenge our imagination even further. Could there have been something before the Big Bang? Some models propose a cyclic universe, endlessly expanding and contracting through a series of Big Bangs and Big Crunches. Others imagine a multiverse, where our universe is just one bubble among countless others, each with its own laws of physics and constants. There are even ideas suggesting the universe emerged from a quantum fluctuation in a timeless vacuum, spontaneously popping into existence. These possibilities are deeply fascinating, but extremely difficult to test. For now, we know only that the Big Bang happened, that space and time began their journey together, and that everything we see today grew from that single moment. Even today, the universe continues to expand, and something strange is driving that expansion faster and faster. We call this dark energy, an unknown force or property of space that acts as a kind of cosmic repulsion. About 68% of the energy budget of the universe is in this mysterious form, while roughly 27% is dark matter, an invisible substance that does not emit or absorb light, but reveals itself through its gravitational pull. Ordinary matter, the kind that makes stars, planets, and people, is only about 5% of the total. The discovery of dark energy in the late 1990s shocked scientists. Until then, many thought the universe's expansion might slow down and eventually reverse under the pull of gravity. But measurements of distant supernovae showed the opposite. The expansion is accelerating, pushed apart by something we still do not understand. Whether dark energy is a property of space-time itself, or the effect of an unknown field, remains one of the greatest mysteries in modern science. Welcome, Cosmic Explorer. Tonight, let us journey together through time and space to explore one of the most profound and fascinating stories of all, the story of how the universe began. The Big Bang Theory is far more than a scientific idea. It is a window into our deepest questions about existence, time, and the laws of nature. How did everything emerge from what seems like nothing? How could a single instant give rise to billions upon billions of galaxies, stars, planets, and life itself? Together, we will look back nearly 13.8 billion years to the moment when time and space themselves were born, and follow the unfolding of the cosmos step by step, as it evolved from a seething fireball of energy into the majestic universe we know today. Before the Big Bang, There was no universe as we understand it. No stars, no planets, no light, and not even darkness, because there was no space in which darkness could exist. There was no time, no measure of before or after. There was simply nothing, not even emptiness. This is one of the hardest ideas for the human mind to grasp, because we are so used to thinking of nothing as a kind of empty space, but even that is already something. True nothingness is beyond our imagination. Yet somehow, about 13.8 billion years ago, something happened. From a point smaller than an atom, a singularity of unimaginable density and heat, the universe began to expand. This was not an explosion in space, but rather the birth of space itself, a rapid stretching and unfolding of the very fabric of reality. In the very first fractions of a second, the universe was an inferno of energy. Temperatures reached beyond what our minds can comprehend, trillions upon trillions of degrees. All four fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, may have been unified into a single superforce, acting in ways no human equations can fully describe. In this unimaginable chaos, the laws of physics themselves were not yet as we know them. Then, in an instant so brief that it defies belief, the universe underwent an extraordinary transformation known as cosmic inflation. In less than a trillionth of a second, the universe expanded exponentially, growing from far smaller than an atom to something the size of a grapefruit, or even larger. This inflation smoothed out any wrinkles or irregularities, leaving behind a nearly uniform cosmos, but with tiny fluctuations in energy density. These tiny differences, created by quantum fluctuations, would become the seeds of all the structure we see today, from galaxies to clusters to vast filaments stretching across the cosmos. As inflation ended, the universe continued to expand, but at a slower rate. In those first microseconds, the energy of the early universe began to transform into particles, quarks, leptons, photons, gluons, and other fundamental entities that make up the building blocks of matter. The temperatures were still so high that these particles existed in a kind of superheated plasma, colliding, transforming, annihilating, and reappearing again in a wild dance of creation. Within about 1 microsecond, quarks began to combine into more stable structures, protons and neutrons. These particles are the cores of atoms, the essential ingredients of ordinary matter. But even these were still immersed in an ocean of radiation, unable to join with electrons to form whole atoms because the universe remained too hot. 1 second after the Big Bang, something remarkable happened. Neutrinos, those ghost-like particles that hardly interact with anything, decoupled from matter and began to travel freely through space. Today, these primordial neutrinos still drift through the universe, almost completely invisible, a silent relic of that first second. Meanwhile, a slight imbalance emerged in the amounts of matter and antimatter. For reasons not yet fully understood, matter gained a tiny advantage. If matter and antimatter had existed in perfect balance, they would have annihilated each other completely, leaving only pure energy. But thanks to this slight asymmetry, a tiny bit of matter was left behind enough to form everything that followed: stars, planets, and living beings. By about 3 minutes after the Big Bang, conditions had cooled enough for nuclear fusion to begin. Protons and neutrons collided and fused to form the first atomic nuclei, mostly hydrogen and helium, with trace amounts of lithium and beryllium. This brief but crucial moment is known as primordial nucleosynthesis. It lasted only a few minutes, but it produced the raw material that would one day become stars. For the next 380 years, the universe was a dense, hot, opaque plasma of nuclei, electrons, and photons. Light could not travel freely because it constantly bounced off free electrons, scattering again and again. The universe was glowing, but nothing could see through the fog. As the expansion continued, the temperature dropped steadily, until at around 380 years, the universe reached about 30 Kelvin. At this point, the nuclei could finally capture free electrons to form neutral atoms, mostly hydrogen and helium. When that happened, the universe became transparent, and light could finally travel without constant scattering. That ancient light is still traveling today, stretched by the expansion of space into microwaves, and we observe it as the cosmic microwave background. This afterglow is a kind of baby picture of the universe, showing us what the cosmos looked like only 380 years after its birth. When scientists study it, they see tiny temperature variations, the same fluctuations seeded during inflation that eventually grew into galaxies and cosmic structures. Thanks to missions like COBE, WMAP, and Planck, we now have incredibly detailed maps of this cosmic background, allowing us to understand the universe's age, shape, and composition with great precision. After this release of light, the universe entered what is often called the cosmic dark ages. There were no stars yet, only vast clouds of neutral hydrogen and helium drifting through space. Gravity began to gather these atoms into denser clumps, forming the first structures. Over hundreds of millions of years, these clouds collapsed further under their own weight until, at last, nuclear fusion ignited and the first stars were born. These first stars, known as population 3 stars, were very different from our familiar Sun. They were huge, hundreds of times more massive, burning incredibly hot and bright, and living extremely short lives. In their cores, they forged heavier elements such as carbon, nitrogen, and oxygen, which the Big Bang itself could not make. When these stars exploded as supernovae, they scattered these new elements into space, enriching the cosmos and allowing later generations of stars and planets to form. Galaxies began to take shape, gathering billions of stars together in magnificent structures bound by gravity. Over billions of years, these galaxies merged, collided, and evolved into the vast galactic clusters and superclusters we see today. A web of filaments and voids emerged, forming a breathtaking cosmic architecture on scales almost impossible to grasp. Our own Milky Way is one spiral galaxy among perhaps 2 trillion galaxies in the observable universe. It formed over many billions of years, building up its stars through countless mergers and bursts of star formation. Roughly 4.6 billion years ago, in a quiet region of one of its spiral arms, our Sun was born, surrounded by a disk of leftover dust and gas. From that disk, 8 planets and countless smaller bodies coalesced, including Earth, the only place we know of so far that hosts life. All the elements in our bodies, the carbon in our cells, the calcium in our bones, the iron in our blood, were forged in ancient stars that lived and died before the Sun was even born. In a very real sense, we are made of stardust, the product of billions of years of cosmic recycling. When you look up at the night sky, you are seeing the descendants of the Big Bang shining back at you across unimaginable gulfs of time. As modern astronomy advances, we have developed tools to look deeper and deeper into this history. Powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, allow us to see galaxies forming only a few hundred million years after the Big Bang. We can watch the cosmic dawn unfold, witness the birth of the first black holes, and measure how galaxies grew and evolved. Each new observation helps refine our picture of the Big Bang and the laws of nature that govern our universe. The Big Bang theory is supported by an extraordinary array of evidence. We see the cosmic microwave background, the lightest elements in precisely the abundances predicted by primordial nucleosynthesis, and the large-scale structure of galaxies matching the patterns seeded by inflation. We see the universe expanding today, confirmed by the redshift of distant galaxies, a discovery first made by Edwin Hubble in the 1920s. Taken together, these observations form one of the most successful and far-reaching scientific models ever created. Yet mysteries remain. The Big Bang Theory describes what happened after the expansion began, but not exactly what triggered it. Did the singularity truly exist? Or is that simply a sign that our current physics breaks down at those extreme conditions? Some scientists think quantum gravity might one day explain the very first instant, uniting general relativity with quantum mechanics. Until then, the precise cause of the Big Bang remains unknown. Other questions challenge our imagination even further. Could there have been something before the Big Bang? Some models propose a cyclic universe, endlessly expanding and contracting through a series of Big Bangs and Big Crunches. Others imagine a multiverse, where our universe is just one bubble among countless others, each with its own laws of physics and constants. There are even ideas suggesting the universe emerged from a quantum fluctuation in a timeless vacuum, spontaneously popping into existence. These possibilities are deeply fascinating, but extremely difficult to test. For now, we know only that the Big Bang happened, that space and time began their journey together, and that everything we see today grew from that single moment. Even today, the universe continues to expand, and something strange is driving that expansion faster and faster. We call this dark energy, an unknown force or property of space that acts as a kind of cosmic repulsion. About 68% of the energy budget of the universe is in this mysterious form, while roughly 27% is dark matter, an invisible substance that does not emit or absorb light, but reveals itself through its gravitational pull. Ordinary matter, the kind that makes stars, planets, and people, is only about 5% of the total. The discovery of dark energy in the late 1990s shocked scientists. Until then, many thought the universe's expansion might slow down and eventually reverse under the pull of gravity. But measurements of distant supernovae showed the opposite. The expansion is accelerating, pushed apart by something we still do not understand. Whether dark energy is a property of space-time itself or the effect of an unknown field remains one of the greatest mysteries in modern science. The journey from the Big Bang to the modern universe is also a journey of increasing complexity. In the beginning, there was only energy, then simple particles, then atoms. Atoms gathered to form stars. Stars made new elements. Elements combined to form planets. And on at least one of those planets, molecules became life. Over billions of years, that life became conscious enough to look back across time and ask, where did we come from? It is one of the most moving parts of the Big Bang story that the cosmos produced beings capable of contemplating its own birth. Imagine for a moment the first stars lighting up, ending the long cosmic dark ages. Their ultraviolet light, so intense, began to carve away the fog of neutral hydrogen, making the universe transparent once again. These stars lived fast and died young, exploding and spreading heavier elements everywhere. In their deaths, they created the conditions for the second generation of stars and for the building blocks of planets and eventually biology. Each cycle of star birth and death enriched the universe a little more until by the time our sun formed, the ingredients for life, carbon, oxygen, nitrogen, iron, were plentiful. Our solar system formed from a swirling disk of gas and dust, orbiting a new, stable yellow star. Gravity sculpted that disk into planets, moons, comets, and asteroids. On Earth, conditions were just right for complex chemistry to thrive. Water collected in oceans, lightning and sunlight sparked reactions among simple molecules, and over time, those molecules organized themselves into self-replicating forms. From those first living cells, a cascade of evolution began, leading eventually to humans and to you, listening to this story. Every step of that path, every twist of cosmic history, traces back to the Big Bang. Without the universe's expansion, there would be no cooling to allow atoms to form. Without primordial nucleosynthesis, there would be no hydrogen or helium. Without the first stars, there would be no carbon or oxygen. Without billions of years of stable cosmic environments, there would be no time for life to evolve. The Big Bang is not just the start of space and time, but the start of every possibility that followed. Today, when scientists look at the sky, they see evidence of this story in every direction. The cosmic microwave background bathes the universe with a faint glow, only a few degrees above absolute zero, a memory of its hot, dense past. Galaxies spread out across space in patterns that match the tiny variations in that background light. Observations of distant supernovae confirm that the universe is still expanding, faster and faster, propelled by dark energy. Everything fits together like an enormous cosmic jigsaw puzzle, giving us confidence that the Big Bang theory is correct, even if some pieces are still missing. Among the most fascinating open questions is the true nature of dark matter. We know it must exist because its gravity shapes galaxies and galaxy clusters, holding them together when ordinary matter alone could not. We see its effects through gravitational lensing, where light from background galaxies is distorted by invisible clumps of mass. Yet no one has detected a dark matter particle directly. Experiments deep underground and in space are searching for these elusive particles, but so far they remain hidden. Perhaps they are some new kind of particle, beyond the standard model of physics, or perhaps our ideas about gravity need revision on cosmic scales. Dark energy, too, remains a mystery. It accounts for nearly 70% of the universe's energy budget, yet we cannot explain what it is. It could be a property of space itself, a cosmological constant, or a dynamic field that changes over time. It might even reveal a completely new layer of physics, one we cannot yet imagine. Understanding dark energy is one of the biggest challenges facing 21st century cosmology, and solving it could change our picture of the entire universe. Another deep puzzle is the very beginning of the Big Bang. As we trace the expansion back, the universe gets hotter and denser until eventually our equations break down. At that singularity, general relativity predicts infinite density and zero size, but infinities usually mean our models have reached their limits. A theory of quantum gravity, uniting Einstein's description of curved spacetime with quantum mechanics, may someday show us what really happened. Until then, the singularity remains a mystery, a signpost pointing to new physics we have yet to discover. Some researchers imagine that the Big Bang was not a beginning, but a bounce from an earlier contracting universe. In that scenario, the cosmos might go through endless cycles of expansion and contraction, avoiding a true beginning or end. Other scientists wonder if the universe arose from a quantum fluctuation in a kind of timeless foam, where countless possibilities constantly flicker in and out of existence until one of them inflates into a whole universe. In these views, the Big Bang is not the absolute origin, but a transition from one state to another. These questions touch the boundary between science and philosophy. They ask what it means for time to begin, whether causality even applies outside the universe, and whether there could be a before without time. They force us to think beyond everyday experience, to imagine realities that our language struggles to describe. And yet, even asking such questions is a triumph, a sign of how far human curiosity has carried us. In our time, we stand on the shoulders of generations of thinkers who tried to understand the cosmos. Ancient astronomers tracked the motions of the planets. Medieval scholars argued about the infinite. Early modern scientists measured the speed of light and the structure of atoms. All of them paved the road to our modern understanding of the Big Bang. Names like Einstein, Hubble, Lemaitre, Gamow, and Hawking are part of that tradition, each adding a piece to the great mosaic of cosmic knowledge. Albert Einstein's equations showed that the universe could be dynamic, expanding, or contracting. Georges Lemaitre, a Belgian priest and physicist, proposed that the universe began from a primeval atom, an idea that foreshadowed the Big Bang theory. Edwin Hubble's observations proved that galaxies were moving away from each other, giving the first clear sign of an expanding cosmos. Later, Arno Penzias and Robert Wilson discovered the cosmic microwave background by accident, hearing its faint hiss with their radio antenna and realizing it was the echo of the Big Bang. These breakthroughs reshaped our worldview, showing that the universe has a history and is still changing. The discovery of the accelerating expansion in 1998 using distant supernovae was another revolution. It revealed that a mysterious dark energy dominates the fate of the cosmos. That discovery earned the 2011 Nobel Prize in Physics, and it set cosmology on a new path, trying to understand why the universe is not just coasting but speeding up. All of these advances have depended on technology as well as theory. Telescopes on mountaintops, satellites in orbit, particle colliders buried underground, all are tools to look back in time, to recreate the conditions of the early universe, and to test our ideas. We have learned to measure tiny ripples in microwave light, to capture gravitational waves from merging black holes, to map the positions of galaxies across billions of light years. The scale and precision of these projects are breathtaking, a tribute to human cooperation and vision. Yet even with all this progress, the Big Bang continues to hold secrets. One is why the universe appears so uniform on the largest scales, yet has enough small imperfections to form galaxies. Inflation explains this beautifully by stretching out the cosmos and spreading quantum ripples to cosmic size. But inflation itself raises questions. What started inflation? What ended it? Could there be other inflationary bubbles beyond our observable patch, each a separate universe with different laws? Some call this a multiverse, an idea both thrilling and controversial. Testing the multiverse is hard because, by definition, other universes would lie beyond our cosmic horizon. But some physicists hope that subtle signatures, perhaps in gravitational waves or patterns in the cosmic background, might hint at collisions between our bubble and others. If so, it would expand our notion of reality unimaginably, showing that the Big Bang was just one act in a far grander cosmic drama. Even if we never find such evidence, the Big Bang itself is a triumph of reason. From a faint microwave glow, from the motions of galaxies, from the abundances of light elements, we have reconstructed a history stretching back almost to time zero. That is a stunning human achievement, a triumph of curiosity and logic, of observation and imagination. Some people find the idea of the Big Bang unsettling. It implies a beginning, and beginnings often make us ask about causes and purposes. Why this universe? Why these laws of physics? Science does not yet answer the why, only the how, but it is a powerful start. The more we learn about the how, the more we can refine our deeper questions about meaning and existence. In the vast sweep of time, civilizations rise and fall, species appear and vanish, but the universe goes on. Its story is written in starlight, in the cosmic background glow, in the gravitational pulls of unseen masses. We are reading that story, line by line, discovering our place within it. It is a story that began with the Big Bang and will continue long after our planet is gone. Your presence in this story is itself amazing. The odds against life arising, against consciousness developing, are staggering. Yet here you are, able to listen, able to think, able to wonder about a time when there was no time, a place where there was no place. That sense of wonder is one of our greatest gifts, a spark of the universe reflecting on itself. If you ever feel small, remember that you are connected to every atom, every galaxy, every bit of cosmic history. You are the outcome of 13.8 billion years of evolution, of stars forging elements, of planets coalescing, of molecules combining, of cells adapting. You are not apart from the universe, you are the universe, conscious and aware, woven from its very fabric. Let us now take a deeper look at the great chain of events that followed the Big Bang, slowly transforming a hot plasma into the breathtaking cosmic architecture we see today. In the first few minutes, as the primordial nucleosynthesis concluded, the universe was left with a composition of about 75% hydrogen and 25% helium by mass, with just traces of lithium and beryllium. These simple elements were the raw materials of everything to come. For hundreds of millions of years, the universe had no stars to shine light upon its growing structures, only these gases slowly pulling together under the patient work of gravity. Gravity is the silent architect of the universe. It tugged on tiny differences in the distribution of matter, gently but inexorably drawing material together. Slightly denser regions gathered more mass, growing into even denser knots, while emptier regions became cosmic voids. Over time, these knots became the first dark matter halos, pulling in ordinary matter along with them. Inside these cradles, clouds of hydrogen and helium collapsed until the pressures and temperatures were high enough to ignite nuclear fusion, giving birth to the very first stars. These first stars were nothing like the sun. They burned tens of thousands of times brighter, living fast and dying young, some in only a few million years. Their enormous masses made them unstable, prone to powerful supernova explosions, or even collapsing directly into black holes. But in their short lifespans, they created the first carbon and oxygen, enriching the universe with elements that would be essential for later generations of stars, for rocky planets, and eventually for life. As these massive stars ended their lives, their violent deaths also compressed surrounding clouds of gas, triggering new rounds of star formation. This recycling of matter is the heartbeat of cosmic evolution. Each generation of stars added new elements to the interstellar medium, steadily increasing the diversity of chemistry in the universe. By the time our solar system formed, about 4.6 billion years ago, the galaxy had been enriched with enough heavy elements to build rocky worlds, oceans, and even the complex molecules needed for living cells. Our planet, Earth, is a child of that cosmic heritage. Its iron core, its silicon crust, its carbon-based life, all are products of ancient stars. The water in your body contains hydrogen created in the first 3 minutes of the Big Bang. The oxygen you breathe was made in a star long before the sun was born. Every cell in you is a microcosm of cosmic history, an echo of processes that stretch back to the universe's first second. This profound connection is not poetic exaggeration but a scientific truth. When you hold a stone, you hold a record of billions of years of nuclear reactions and cosmic processes. When you look in a mirror, you see a being shaped by gravity, chemistry, and time, a being who can wonder about where it all began. In the larger scheme of the universe, humans appeared only in the final instant. If the entire 13.8 billion year history of the cosmos were compressed into a single calendar year, with the Big Bang at midnight on January 1, our species would emerge only in the last seconds of December 31. Everything we call history, the building of pyramids, the invention of writing, the rise of science, would occupy a microscopic sliver of that cosmic year. And yet, in that instant, we have reached out with telescopes and theories to piece together the entire story of time. Today's astronomers can look back in time by observing distant galaxies whose light began traveling toward us billions of years ago. The farther we look, the closer to the Big Bang we see. These ancient galaxies show us how stars were forming in the early universe, how black holes grew, how the elements were forged. They reveal a cosmos in motion, forever changing and evolving. Meanwhile, scientists on Earth use powerful particle accelerators to study the conditions of the first microseconds after the Big Bang. By smashing protons together at nearly the speed of light, they recreate tiny flashes of primordial plasma, glimpses of a universe as it was in its infancy. These experiments help test theories about how quarks combined into protons and neutrons, and about how the fundamental forces separated from their unified state. One great hope is to find a complete theory of quantum gravity, which would explain the Planck era, the earliest instant of all, before even inflation took place. Right now, general relativity describes the large-scale universe beautifully, while quantum mechanics rules the tiny world of particles. But at the beginning of time, these two realms overlap, and our equations fail. A unifying theory could answer what space and time really are, and whether they might emerge from something even more fundamental, like vibrating strings or spin networks. Some researchers imagine that space-time itself is not fundamental but emergent, like how temperature is a property of many atoms rather than a single particle. In these views, the Big Bang was a phase transition, like water freezing to ice, and space-time appeared as a new state of matter. These are speculative but fascinating concepts, showing how creative science can be when confronting the deepest mysteries. No matter which theory turns out to be true, the evidence for a hot, dense beginning is overwhelming. The cosmic microwave background matches predictions with incredible precision, showing slight variations that grew into the web of galaxies. The relative amounts of hydrogen, helium, and lithium perfectly match what nuclear reactions in the first minutes should have produced. The distribution of galaxies agrees with the seeds laid down by inflation. Together, these lines of evidence build a coherent and powerful story of the universe's origin. And yet, the Big Bang is not the final word. It is the beginning of our knowledge, but also the start of new questions. What is the ultimate fate of the cosmos? Will dark energy tear it apart, or will something unexpected happen? Are there other universes beyond our horizon? Could entirely new physics be waiting to be discovered in subtle patterns of radiation or in the whispers of gravitational waves? Science is a journey, not a destination. With every answer, new mysteries open up. That is what makes the Big Bang so compelling. It is both a triumph of human understanding and a reminder of how much we still have to learn. When you stand outside on a clear night and look at the stars, you are witnessing a fossil of cosmic history. Those pinpoints of light began their journey across the universe long before you were born, sometimes before the Earth even existed. Their photons have traveled through the stretching fabric of space, carrying messages about the past. When you catch their light with your eyes, you are connecting to an ancient, unbroken chain of cosmic events that began at the Big Bang. As we look forward, new generations of telescopes will open even more windows onto that chain of events. Giant radio arrays will map the dark ages between recombination and reionization, revealing how the first galaxies lit up the sky. Space-based gravitational wave observatories will listen for ripples from the earliest seconds of inflation. Even more sensitive microwave telescopes may spot patterns left behind by collisions of our universe with other bubbles in the multiverse, if such collisions ever happen. Each observation brings us closer to understanding the full story of how everything came to be, and each discovery will probably raise more profound questions. That is the nature of science, an ever-deepening spiral of wonder, evidence, and mystery. If you think of the universe as a book, then the Big Bang is page 1. We have read many chapters since, and we are writing new ones every day. But no matter how far we go, we always look back to that first page, trying to read the faint, nearly erased handwriting that began the story. Cosmology is a humbling subject. It shows us how tiny we are compared to the vastness of space, yet how connected we are to all of it. The atoms in your hand were once forged in a star. The hydrogen in your water was made seconds after the Big Bang, and the iron in your blood was born in a supernova. The calcium in your bones, the phosphorus in your DNA, all owe their existence to cosmic processes stretching back 13.8 billion years. When you breathe, you take in oxygen made in ancient stellar furnaces. When you move, you use energy stored in molecules powered by sunlight, which in turn was made possible by nuclear reactions in the core of a star. Every heartbeat echoes the deep rhythm of the cosmos, a beat that began in that first great expansion. In this way, the Big Bang is not distant or abstract. It is personal. It is the story of your atoms, your breath, your consciousness. It is the reason you exist at all. The same physics that governs galaxy clusters also shapes the neurons firing in your brain. You are, quite literally, a self-aware piece of the universe reflecting on itself. Think of what that really means. The universe woke up. From pure energy and chaotic particles, from exploding stars and drifting dust, emerged molecules that could copy themselves, that could learn, adapt, and evolve. Over billions of years, those molecules organized into living cells, into plants, animals, and eventually humans, able to look back across time and wonder about their place in the cosmic story. If you consider the odds, it is astonishing that such complexity could arise from a universe that began as a hot, dense soup of simple particles. And yet, given enough time and the right physical laws, complexity seems inevitable. Gravity pulls matter together, nuclear forces build elements, chemistry creates new possibilities, and eventually, evolution tries out endless combinations until life emerges. That is the true legacy of the Big Bang, not just a burst of light and energy, but a universe with the potential to become self-aware. Scientists today use powerful computer simulations to retrace this path from simplicity to complexity. They model how gas clouds collapse to form the first stars, how supernova explosions enrich their surroundings, how galaxies grow through collisions and mergers, and how black holes influence the flow of matter. These simulations are so detailed they can recreate the large-scale structure of the universe, matching observations with amazing accuracy. They show how the cosmic web of filaments and voids arose from tiny fluctuations in the Big Bang's aftermath, stretched by inflation to enormous scales. In these simulations, you see how galaxies gather into clusters, drawn together by dark matter's invisible grip. You see how star formation ignites, dies, and reignites in waves, sculpted by black holes at galactic centers that feed on matter and unleash powerful jets of energy. These cosmic patterns are the fingerprints of gravity at work, guided by the seeds laid down in the earliest moments of the universe. Our understanding of cosmic history grows richer every year. The James Webb Space Telescope is revealing infant galaxies never seen before, giving us clues about how fast the first stars formed. Meanwhile, particle physicists continue to search for signs of new particles that might explain dark matter or even hint at unknown forces beyond the standard model. Every experiment, every new telescope, is another step toward filling in the blanks of the Big Bang story. Still, the deepest mysteries may always be out of reach. We may never fully know what happened before the Planck era, if there even was a before. We may never be able to test ideas about other universes or about what set inflation in motion. And yet there is something beautiful in accepting that some mysteries endure, driving us to keep asking, keep exploring, and keep learning. When you look at the night sky, you might see stars as static points of light, but in reality, they are messages from the past. Some of those stars no longer even exist, having exploded or faded, but their light is only now arriving. You are witnessing ancient history, written across space and time. Every photon you catch on your retina began its journey long before you were born, crossing billions of kilometers through the expanding universe, a cosmic messenger carrying information about where and when it came from. Think of the incredible journey of those photons. Imagine one leaving a star a billion years ago, traveling through a universe of growing galaxies, crossing filaments of dark matter, bypassing clusters of galaxies, unaffected by anything except the stretching of space itself, until at last it arrives in your eye. In that moment, you complete its journey by becoming aware of it. In a sense, you and that photon are part of the same story, both born from the same cosmic processes that began with the Big Bang. If you could stand outside time and watch the entire history of the universe as a film, you would see a breathtaking sequence, a flash of creation, rapid inflation, cooling plasma, recombination releasing the first light, the slow collapse of gas into stars, galaxies igniting, elements forming, planets emerging, and finally, life stirring in warm oceans on a rocky world. You would see extinctions, adaptations, intelligence, and consciousness until, at the very end of the film, a species asks, "How did all this begin?" That species is us, still trying to read the first frame of the movie. Perhaps that is what makes cosmology so powerful. It gives us a sense of belonging. It tells us that we are not random accidents, but participants in a lawful, evolving cosmos. We follow the same physical rules as the stars, the same chemistry as the galaxies, the same mathematics as the expanding fabric of space. In that sense, the Big Bang story is the story of us all. And what about the future? If dark energy continues to accelerate the expansion, then eventually the night sky will grow empty. Distant galaxies will move away faster than light, becoming forever unreachable. In trillions of years, only our local group of galaxies will remain visible. Stars will burn out, planets will freeze, and black holes will evaporate. On even longer timescales, matter itself may decay, leaving behind only a thin mist of radiation. This is one possible end, a universe grown cold, silent, and dark, an eternal night following a bright dawn. But maybe the story will surprise us. Maybe dark energy will change. Maybe new physics will intervene. Maybe intelligent life will find ways to reshape its environment, to light new fires even after the stars die. These are wild speculations, but they remind us that the universe is a dynamic place and that the story begun by the Big Bang is still being written. In the meantime, we keep learning. We keep listening for gravitational waves, studying the faintest patterns in microwave light, searching for signals of dark matter, building instruments that push the limits of sensitivity and scale. Each discovery is like a candle, illuminating one more piece of the cosmic puzzle. It is an act of hope, an act of curiosity, an act of profound connection to our place in the cosmos. Whenever you feel overwhelmed by daily worries, think about this. The atoms in your body were made in stars. The energy that powers your thoughts has traveled across billions of years. You are connected to galaxies beyond counting, to forces deeper than imagination. That perspective can be comforting, a reminder that your life, however small it may feel, is part of a cosmic process stretching back to the dawn of time. The Big Bang is more than a scientific model. It is a bridge between our existence and the deepest workings of nature. It tells us that the universe has a history, that things change, and that from the simplest beginnings, complexity and beauty can emerge. It tells us that we are born from the same universe we study, made of its elements, shaped by its laws, and inspired by its grandeur. This story will continue to unfold as long as there are minds to ask questions and eyes to look at the stars. Each generation will add new chapters, build new instruments, dream new dreams. The Big Bang will remain at the center of that story, a constant reminder of our shared origin. Let us now travel even deeper into the scientific legacy of the Big Bang, reflecting on how humanity pieced together this remarkable picture. 100 years ago, most scientists believed the universe was static and eternal. The idea of a beginning seemed strange and even disturbing. Einstein himself introduced a cosmological constant to keep his equations from predicting expansion, because he assumed the universe must be unchanging. Then came the observations of Edwin Hubble, who saw that distant galaxies were receding from us, their light stretched toward the red end of the spectrum. The farther away they were, the faster they moved. This was unmistakable evidence that space itself was expanding. At first, some scientists resisted the idea. It took years of further observations, especially the discovery of the cosmic microwave background in 1965, to convince nearly everyone that the universe had indeed started in a hot, dense state. Since then, the Big Bang model has become one of the pillars of modern science, tested and refined by thousands of experiments and observations. Missions like COBE, WMAP, and Planck mapped the cosmic background radiation with extraordinary precision, revealing tiny temperature variations that match the seeds of galaxies seen today. Observations of light element abundances confirmed what Big Bang nucleosynthesis predicts. Large-scale surveys of galaxies showed how matter clumps under gravity, matching the patterns seeded by inflation. All these clues come together in a consistent, powerful story. The universe was once small, hot, and dense, and has been expanding and cooling ever since. Inflation theory, proposed in the 1980s by Alan Guth and others, beautifully solved problems like why the universe appears so uniform and flat. It explained how tiny quantum fluctuations could be blown up to cosmic size, seeding the web of galaxies. It even suggested the possibility of multiple inflationary bubbles, the multiverse, each with its own laws of physics. Although inflation is still being tested, it has become the leading explanation for how the universe smoothed out in its earliest moments. Today, scientists continue to hunt for signs of primordial gravitational waves, faint ripples from inflation that could be imprinted on the polarization of the cosmic microwave background. Detecting those would be a major breakthrough, revealing evidence of physics at energies far beyond any particle accelerator on Earth. It would be a glimpse into forces and processes active in the first trillionth of a second. Meanwhile, underground laboratories search for dark matter particles, hoping to catch one of these mysterious bits of mass that pass through us by the trillions every second but barely interact. Massive detectors filled with noble gases, or built of cryogenic crystals, wait patiently in deep mines, shielded from cosmic rays, hoping for the tiniest flash of light that might reveal dark matter's nature. New telescopes like the Vera C. Rubin Observatory will map billions of galaxies in exquisite detail, tracking how structure grows over cosmic time. Radio telescopes will scan the hydrogen line across vast distances, revealing the era before the first stars formed. Each of these projects helps test and refine the Big Bang picture, adding precision to our timeline of cosmic history. At the same time, theorists push to expand our models. They ask whether dark energy might evolve, whether extra dimensions could change gravity, whether subtle patterns in the cosmic background might hint at unknown particles. They build frameworks like string theory, which proposes that all particles are tiny vibrating strings in higher dimensional space, or loop quantum gravity, which imagines space itself as a web of quantum threads. These ideas are far from proven, but they show the bold creativity of scientists trying to reach beyond the limits of current knowledge. One thing is certain: the Big Bang is not the end of the story. It is the beginning of everything we can see and touch, the root of all cosmic evolution. But it also marks the beginning of our questions. What sparked the expansion? Why do the laws of physics have the values they do? Why is there something rather than nothing? These questions are as deep as any asked in philosophy, and they remind us that science and wonder are forever linked. If you stand under a starry sky and let your mind drift across the eons, you might feel a strange mix of humility and pride. Humility, because the universe is vast beyond measure, and we are small. Pride, because even the smallest mind can hold the entire universe within its imagination. That is the miracle of consciousness, forged by cosmic forces, yet able to contemplate those very forces. Imagine the Big Bang again if you can, a state with no space, no time, a singularity of infinite density then, a burst of expansion so fast that it created all the room needed for galaxies, stars, planets, and life. In the first fractions of a second, all the matter and energy of the future was present, but in a raw, chaotic form. From that primal soup, patterns arose, guided by the laws of physics. Forces separated, particles combined, light emerged, atoms formed, structures gathered, and in time, stars lit up the darkness. That is the arc of cosmic evolution, from simplicity to complexity, from chaos to order, from unconscious matter to thinking beings. The Big Bang lit the spark, and the universe has been unfolding ever since, in ways more intricate than any myth or legend humans ever dreamed. In the earliest cultures, people invented stories to explain why the world exists. They spoke of gods, of cosmic eggs, of giant serpents. These myths were poetic, rich with meaning, but they had no measurements, no experiments, no tests. Modern cosmology, by contrast, builds its stories on observation, mathematics, and logic, and yet it is no less wondrous. In fact, it may be even more awe-inspiring to realize that a universe of such elegance and complexity could arise from a single instant, governed by simple, consistent laws. Our ancestors looked up and saw the same stars you see today. They did not know their light had traveled across billions of years, or that their atoms were born in dying suns. They did not know those stars were the descendants of a cosmic explosion older than the Earth itself. But they wondered, just as we do. That continuity of wonder is part of being human. So, when you listen to the story of the Big Bang, you are taking part in an ancient quest to know where we come from, what we are, and what might lie ahead. It is a quest that links you to the first astronomers, to the first philosophers, to every person who ever looked at the sky in curiosity. In the future, our descendants may know much more than we do. They may find evidence of a multiverse. They may detect the decay of dark matter. They may understand the origin of time itself. Or they may discover new puzzles, deeper still, hidden in the structure of reality. That is the promise of science. There is always more to learn. Meanwhile, you can stand in quiet awe of what we already know. That everything around you, every tree, every mountain, every ocean, owes its existence to a moment of pure creation, to a universe that began as a single expanding point. That moment gave birth to space, time, energy, matter, and eventually to life. That moment is written in the background radiation, in the elements of your body, and in the patterns of galaxies stretching across the night sky. The Big Bang is not just about physics, it is about meaning. It shows us that even the simplest beginnings can lead to unimaginable complexity. It shows us that order can emerge from chaos, that tiny quantum ripples can become vast cosmic structures, and that from inanimate matter can arise conscious life. In that sense, the Big Bang is a profound inspiration. It tells us that change is possible, that small seeds can grow into great trees, that humble origins do not limit what is possible. Whether in nature, in history, or in your own life, that lesson resonates. Beginnings matter, and from them, anything can flow. As we stand now, halfway through the age of our star, on a small planet in the Milky Way, we have the privilege of knowing something about our cosmic past. We have measured the faint afterglow of the Big Bang. We have mapped the structures born from it. We have traced the journey of atoms from stars to life. That knowledge is a treasure, one that future generations will build upon. And we are not done. New eyes will look to the heavens, new minds will ask new questions, and the universe will continue to reveal its secrets. The story that began with the Big Bang is only in its opening chapters, and we are its authors as well as its readers. Let us continue then to follow the incredible unfolding of the universe from that first instant onward. After the Big Bang released its tremendous energy, the universe expanded and cooled, but it did not become quiet. Instead, it continued to change on every scale, in every corner. The simplest forms of matter began to group and assemble, drawn by gravity into structures larger and larger. From those structures, galaxies formed, each one a city of hundreds of billions of stars. Some galaxies became giants, gathering up smaller neighbors in colossal mergers. Others, like our own Milky Way, built themselves slowly over billions of years, forming spiral arms filled with gas and stars. In the spaces between galaxies, cosmic filaments stretched like bridges, channeling matter along their lengths, linking together clusters in a vast cosmic web. These filaments emerged from the tiny quantum ripples seeded during inflation, which had been amplified to cosmic scales. Over time, gravity turned those tiny differences into the scaffolding of the universe we see today. The cosmic web is one of the most breathtaking structures ever discovered. Across hundreds of millions of light years, galaxies and dark matter trace patterns that look almost biological, like the filaments of neurons in a human brain. Scientists have marveled at this similarity, wondering if there is a universal principle behind such network structures, a tendency of nature to self-organize into efficient, connected patterns, whether on the scale of a brain or the scale of the cosmos itself. In these galactic cities, stars are born, live out their lifespans, and die, enriching their surroundings with heavier elements. Planetary systems emerge in the disks around new stars, made of recycled dust from earlier stellar generations. Some planets form in stable orbits, with temperatures and chemical compositions that allow complex chemistry. On at least one such world, chemistry became biology, and biology became aware of itself. When you think about it, it is remarkable that the laws of physics permitted such a chain of events. Tiny changes in the strength of gravity, the charges of electrons, or the rules of nuclear reactions would have made a universe without stars, or with only hydrogen, or with no stable atoms at all. Our universe seems finely tuned for complexity to arise, though whether that is coincidence, necessity, or a sign of deeper principles is still an open debate. Some scientists propose the anthropic principle, which suggests we observe this particular universe because only universes with the right conditions for observers can be noticed at all. If there are countless other universes with different laws, most of them may be sterile and lifeless, and we naturally find ourselves in one of the rare, life-permitting ones. Others argue there may be a deeper theory, not yet discovered, that makes our universe inevitable. Regardless of the explanation, the fact is that we live in a universe capable of producing thinking beings, and that is amazing. Every law of nature, every physical constant, every cosmic event since the Big Bang has played a role in bringing us to this moment. From the expansion of space to the cooling of atoms, from the birth of stars to the formation of planets, every step has built on the previous one in a breathtaking sequence of cause and effect. When you stand outside at night and look up, you are seeing the result of those countless steps. The starlight you see is ancient, carrying with it a story billions of years long. Each photon is a messenger, a record of nuclear fusion in a star's core, of a journey through interstellar dust, of travel across an expanding cosmos. When that photon reaches your eye, the chain is complete. A piece of the Big Bang's legacy has arrived in your mind. We often talk about the cosmic microwave background as the baby picture of the universe, but the light from stars is like a family album, showing all the stages of cosmic growth since then. It is a record of how the universe matured, how it built the richness and variety we see today. From faint red dwarfs to brilliant blue supergiants, from swirling spiral galaxies to giant elliptical ones, the diversity of cosmic structures is stunning, and all of it ultimately traces back to the Big Bang. Even our own sun carries that legacy. It is a second or third generation star, enriched with elements made by earlier stars. Its planets formed from dust grains that had been through countless cycles of birth and death. Life on Earth evolved under the steady warmth of the sun, powered by fusion reactions turning hydrogen created in the Big Bang into helium. In that sense, your every heartbeat is driven by energy that originated at the dawn of time. Our technologies, too, rely on cosmic history. The metals in your phone, the silicon in its chips, the rare elements in its battery, all of them were created in ancient stars. The gold in a wedding ring may have come from a neutron star collision billions of years ago, the result of titanic forces merging and blasting heavy elements into space. Everything you touch, everything you use, is made possible by processes born in the first seconds of the universe. Such reflections can be humbling. They remind us how deeply dependent we are on events we could never control, on cosmic conditions far beyond any human influence. And yet they also show how connected we are to the universe, not separate from it, but entirely part of it. That connection is both scientific and spiritual, a reminder that our existence is tied to the same cosmic laws that shape galaxies and black holes. When you learn about the Big Bang, you are learning about yourself. You are learning where the atoms in your hands came from, how the forces holding them together emerged, and how the rules allowing them to form stable matter were written in the first instant of time. This is a knowledge both intimate and grand, touching the deepest parts of human identity. In that knowledge, there is a kind of peace. Even in a universe that may seem cold or indifferent, you are here because it is lawful and ordered, because it allowed complexity, because it gave space for consciousness to arise. That is not a small thing. That is a magnificent, almost miraculous gift, made possible by the events of the Big Bang. If you ever doubt your place in the universe, think of this. You are made of its oldest light and its most ancient elements. You are powered by energy from the fusion of primordial hydrogen. You are the product of cosmic history, made aware, able to reflect and wonder. That alone is reason enough to feel awe. The future of cosmology is wide open. New missions will scan the sky for subtle gravitational ripples from inflation, testing ideas about the earliest fractions of a second. Other satellites will map the polarization of the cosmic background even more precisely, hunting for clues about the energy scale of inflation or even hints of exotic physics like cosmic strings. The search for dark matter will continue, perhaps with new detectors deep underground or with experiments in space looking for annihilation signals. Physicists may yet discover new particles at the Large Hadron Collider or future colliders, revealing hidden symmetries that change how we think about matter. And theorists will keep proposing bold ideas about what happened before the Big Bang, whether in a multiverse, a cosmic bounce, or something stranger still. As all these efforts unfold, the story of the Big Bang will grow ever richer. Like a painting being restored stroke by stroke, its details will sharpen, its colors will deepen, and its meaning will expand. We will never stop asking where it all came from, and in asking, we will keep adding new chapters to the great cosmic epic. You are part of that epic. Every time you wonder, every time you learn, you continue the same drive that pushed the first humans to look at the stars. The Big Bang is not a distant curiosity, it is your heritage. Its energy flows through you. Its rules shape you. Its elements build you. In that sense, you are the universe remembering itself. Let us now imagine for a moment how fragile this chain of cosmic events truly is. If the laws of physics had been even slightly different, the universe might have ended up empty, cold, or chaotic. If gravity were stronger, everything might have collapsed before stars could form. If the strong nuclear force were weaker, atoms could not hold together. If the ratio of matter to antimatter had been more balanced, matter would have vanished completely. The universe would be nothing but light, with no atoms, no chemistry, and no life. Yet the universe did not take those paths. Somehow, through a balance of chance and law, it unfolded in a way that allowed stars to shine, planets to coalesce, oceans to form, and eventually, living creatures to walk the surface of one small world. That is why cosmologists sometimes speak of the fine-tuning problem, asking whether there is a deeper explanation for why the universe is so hospitable to complexity. Some researchers see this as evidence for a multiverse, where countless universes with different physical laws exist, and we simply live in the rare one where things worked out. Others suggest there could be principles we have not discovered yet, rules that require the universe to have these properties. Either way, the fact that you exist to hear this story is a powerful sign that the universe permits, and even encourages, complexity to blossom from simplicity. As time goes on, the universe will continue to change. Right now, stars are still forming, galaxies still grow, and black holes still feed. But in the far future, that will shift. Star formation will slow as the raw gas is used up. Giant galaxies will become islands in a darkening cosmos. Black holes will become the last major actors, slowly evaporating over unimaginable timescales. On scales of trillions, or even quadrillions of years, matter itself might decay, leaving behind a thin haze of radiation. That distant future is almost beyond our comprehension, a time when even the memories of galaxies will have faded, and the universe will be a quiet sea of emptiness. This is one possible end, a heat death, the final echo of the Big Bang's explosive beginning. But perhaps new ideas will change that picture. Maybe physics will discover hidden dimensions or subtle effects that allow energy to recycle. Maybe intelligent life will someday find ways to create new universes, extending the story in ways we cannot even imagine. These are speculations, but they remind us that the future, like the past, can hold surprises beyond anything we have yet dreamed. In our own age, the fact that we can measure, model, and even talk about these questions is remarkable. From the earliest myths of creation to modern equations describing inflation, humans have always tried to trace their origins. The Big Bang story is simply the latest and most powerful chapter in that quest. Think of the incredible chain of minds who built this knowledge. From Newton to Einstein, from Lemaitre to Hubble, from Gamow to Penzias and Wilson, each generation has passed forward a piece of the cosmic puzzle. Their work has shown that science is a shared human enterprise, growing over centuries, rooted in cooperation and curiosity. You, listening now, are part of that chain, benefiting from thousands of years of people who asked questions and refused to settle for easy answers. And there are still big questions left. What is the true nature of time? Did it really begin with the Big Bang, or is time emergent from deeper laws? Why does the universe have 3 spatial dimensions and 1 of time, instead of some other combination? Why do the laws of physics appear so precisely balanced? These are mysteries that blend physics and philosophy, showing that some of our greatest questions lie at the frontier where science meets meaning. Even the question, what happened before the Big Bang, may be based on a misunderstanding, because time as we know it might have begun with the expansion. Some theorists suggest that before is meaningless. The way north of the North Pole is meaningless. Others say there might have been a timeless quantum foam or a previous collapsing universe that bounced into expansion. These possibilities are still untested, but they are a testament to human imagination, pushing beyond the known into the realm of the possible. In the coming decades, new observations may bring clues. Gravitational wave observatories could detect signals from the inflationary epoch, revealing what happened in the first fractions of a second. New maps of the cosmic background's polarization might catch hints of other universes bumping into ours. Powerful particle colliders might uncover hidden symmetries, giving us hints about how the earliest forces split apart. Each experiment is a candle, lighting up a little more of the darkness. And with each candle, we see our place in the universe more clearly. We see that we are small, but not insignificant. We see that we are temporary, but part of something eternal. We see that our brief lives are built on a foundation that stretches back 13.8 billion years and forward for trillions more. Whenever you feel lost, you might look up and remember this story. You are here because the universe had the right conditions to make stars, planets, and life. You are here because atoms, born in the Big Bang, survived and became you. That perspective can bring peace, a sense of belonging, and a reminder of how precious every moment really is. The Big Bang story is not finished. It grows with every telescope, every equation, every curious mind. We will keep refining our models, keep pushing back the horizon of what we know, keep asking why. That is the promise of science. It never stops. As long as there are questions, there will be people searching for answers. And in that search, there is a kind of hope. Hope that we can understand. Hope that knowledge can make us wiser, kinder, more connected to each other and the world. Hope that even in a universe vast beyond measure, meaning can arise from awareness, from cooperation, from wonder. Perhaps the greatest gift of the Big Bang is that it teaches us to think big, to see ourselves as part of something enormous, ancient, and magnificent. To dream beyond the confines of one planet, one moment, one lifetime. That gift is priceless, and it is one we can pass on to every new generation, like a torch carried across the ages. The next time you see the night sky, let these ideas echo in your mind. Know that you are seeing starlight that began its journey long before your ancestors walked the earth. Know that you are built of atoms whose story began at the birth of the cosmos. Know that the thoughts you think now are powered by energy drawn from the oldest hydrogen made in the Big Bang. That connection is real, profound, and beautiful. Let us now reflect on the deeper lessons this cosmic origin story gives us. The Big Bang tells us that the universe has a beginning, that time itself is part of a grand unfolding, and that change is woven into the very fabric of reality. It tells us that nothing stays the same forever, that all things are born, evolve, and one day fade. This is true of galaxies, of stars, of planets, and of life. In a sense, the Big Bang is the ultimate teacher of impermanence, showing us that even the mightiest structures owe their existence to processes of transformation. From the moment of its first instant, the universe has been a place of constant motion. Expansion, cooling, clumping, igniting, exploding, recycling. These processes go on in a cosmic dance that continues to this day. Each new star is both an ending and a beginning, recycling the ashes of what came before into something new. Each galaxy is a city in motion, its stars orbiting, colliding, creating new worlds over billions of years. Even the vast dark matter filaments shift and evolve, shaping the growth of clusters and superclusters. And through all these cosmic processes, tiny blue-green worlds like Earth can appear fragile oases where molecules can gather, where water can flow, where chemistry can blossom into life. Think of how unlikely that is. One small rocky planet, in a safe orbit around a stable star with liquid water and a protective magnetic field, in just the right part of a spiral galaxy and over billions of years. That planet develops creatures who can contemplate the age of the universe. If that does not fill you with awe, nothing will. Our ability to measure, describe, and even imagine the Big Bang is itself a triumph. It shows that tiny primate brains on a small world can develop languages, mathematics, and instruments powerful enough to read the sky like a library, to measure events billions of years ago with astonishing precision. That is not just science, that is a profound testament to what intelligence can achieve. Think about the tools that let us do this. Space telescopes that float far above the blur of Earth's atmosphere, catching faint signals from the earliest galaxies. Particle colliders that smash protons together at nearly the speed of light, recreating conditions a billionth of a second after the Big Bang. Cryogenic detectors deep underground, patiently listening for the whisper of a dark matter particle. Each is an expression of human curiosity turned into technology, pushing back the frontier of ignorance. It is also a story of cooperation. No one person could discover the Big Bang alone. It took centuries of thinkers, experimenters, engineers, programmers, and dreamers, each building on each other's work. Science is a collective human achievement, and the Big Bang Theory is one of its greatest monuments. When you hear that the cosmic microwave background is measured to 1 part in a million, or that we know the universe is 13.8 billion years old with a precision of less than 1%, remember that behind those numbers stand countless people working together across cultures, nations, and generations. That should give us hope, too. If we can understand something so immense, so ancient, perhaps we can also solve the challenges here on Earth. The same spirit of cooperation, the same respect for evidence, the same curiosity, could help us build a better future. The Big Bang reminds us that we share a common origin, that every person is made of the same stardust, born of the same cosmic fireball. We are all family, in the deepest sense imaginable. Looking forward, the questions remain thrilling. How will the universe end? Is there really a big freeze waiting, where galaxies vanish beyond reach and stars go dark? Could there be a big rip, where space tears itself apart? Might something more hopeful lie ahead, like new physics that renews the cosmos in endless cycles? We do not know. But the effort to find out is worth everything. Imagine what a person from 1,000 years ago would think if they could hear this story. That we know about invisible matter shaping galaxies, that we have measured gravitational waves from colliding black holes, that we have mapped light from the first 380 years of the universe. It would sound like magic, and yet it is real, built on observation, logic, and relentless curiosity. You too are part of that chain. Every question you ask, every time you wonder about how things work, you continue the same tradition that brought us from campfire myths to cosmic microwave maps. You are the universe trying to understand itself, and that is one of the most meaningful roles imaginable. So as you prepare to rest, carry with you this thought. You are a child of the Big Bang. Your body is made of its elements, your energy powered by its hydrogen, your mind shaped by its laws. You are a temporary pattern in an ancient flow, beautiful and unique, but deeply connected to everything else. That connection is permanent, no matter how the universe changes. In a way, that is a kind of immortality. The matter that makes you will continue on, becoming part of new stars, new worlds, new forms of life, for billions of years to come. You will rejoin the cosmic story, as everything does. Nothing is lost, only transformed, carried forward by the same universal rules that began in a single instant of unimaginable heat and density. Let that knowledge bring you peace. The universe is vast, but you are part of it. The future is uncertain, but you belong to something enduring. Time marches forward, but you are built of timeless atoms, forged in stars, shaped by cosmic expansion. That is, as close to eternal as anything we know. As our understanding of the Big Bang improves, we will surely find surprises. Perhaps dark energy will turn out to be far more complex than we imagine. Perhaps time itself will reveal hidden dimensions. Perhaps our entire cosmos is one leaf on a vast cosmic tree, whose branches we have only begun to glimpse. These are bold ideas, but that is what the Big Bang inspires. The courage to think big, to ask impossible questions, to look beyond our limits. In the end, that is the true lesson of the Big Bang. It shows us that no question is too large to ask, no mystery too deep to explore. It teaches us to keep going, to keep seeking, to never stop wondering, because from wonder comes discovery, from discovery comes understanding, and from understanding comes meaning. As we bring this vast journey to its close, let us pause and gather all these threads. The Big Bang is not just a theory in a physics textbook. It is the reason there is anything at all, the moment that turned a singular, unimaginable seed of energy into a universe 90 billion light-years across, brimming with galaxies, stars, and worlds. It is the spark that set everything in motion, a spark whose echo still glows in the cosmic microwave background, whispering to us across billions of years. It tells us that from simplicity, complexity can arise. From pure energy, matter can form. From randomness, patterns can emerge. From the laws of physics, life can blossom. And from life, minds can appear, minds that wonder, minds that create, minds that reach for the stars. That is the arc of the Big Bang story, the reason it resonates so deeply in human hearts. Every time you see the sunrise, remember that its light is fueled by hydrogen created in the first 3 minutes of the universe. Every glass of water you drink contains hydrogen older than the Earth itself. Every breath of air carries nitrogen and oxygen born in long-dead stars. Every heartbeat is sustained by the same electromagnetic forces that were forged in the first instant of cosmic time. You are not an observer of the universe, you are the universe, made aware of itself. That simple, profound truth is the gift of cosmology. It reminds you that even in a universe that can feel cold or indifferent, there is deep connection woven through every atom, every law, every moment of existence. Let yourself be amazed by this. The universe is not only stranger than we suppose, it is stranger than we can suppose, as some scientists have said. And yet, with patient observation, careful thinking, and shared effort, we have begun to grasp at least a few of its secrets. We have charted its expansion, mapped its faint microwave glow, measured its age and size, and even traced the creation of its elements. That is a stunning achievement for a species that has been around for only the tiniest blink of cosmic time. One day, someone will carry this story further. They will discover what dark energy really is, or see proof of other universes, or unravel the true nature of time itself. We stand at the beginning of that quest, not its end. Every generation will build upon ours, adding new chapters to this ever-expanding tale. That is a hopeful vision, one that should inspire us to keep learning, keep questioning, keep imagining. As you prepare to rest, let your mind wander through the images of the cosmos, the first fireball of the Big Bang, the gentle ripples of inflation, the cooling plasma that released the cosmic microwave background, the gathering of gas into the first stars, the forging of carbon and oxygen, the building of galaxies, the birth of planets, and finally, the spark of life. All of it is one grand, unbroken story, and you are woven into its tapestry. When you close your eyes, you might picture yourself drifting through intergalactic space, surrounded by the faint glow of 1 trillion galaxies. Each one is a chapter of cosmic history, each star a testament to the power of physics, each planet a possible cradle of life. The peace of that image, the calm of knowing you are part of something vast and beautiful, can stay with you, easing your mind, reminding you that you are never truly alone. In the final analysis, the Big Bang is not just a cosmological event, it is the ultimate beginning. It is the place where time, space, matter, and energy began their journey together, carrying within them the possibility of everything that has happened since. Without it, there would be no light, no life, no thought, no question, and no you. So let this knowledge settle in your heart. From a single moment of unimaginable heat, a universe of extraordinary beauty was born. You are its child. You carry its legacy in every cell. You breathe its history with every inhale, and you dream with the same atoms that once blazed as starlight. May that thought comfort you whenever you wonder about your place in the cosmos. May it remind you that you belong, that you are a product of this universe, that your story and the universe's story are the same. And may it encourage you to keep asking, keep exploring, keep celebrating the mystery of existence. Sleep well, cosmic voyager. Let your dreams wander among the galaxies. Let your imagination soar across the great cosmic web. And let the quiet power of the Big Bang remind you that from the smallest seed, the greatest wonders can grow. Good night, and safe travels through the endless night of stars.